Imagine a better world, where our planet and climate are healthier. We have better energy from better sources and produce better food and wine. A world with understanding of all cultures, where we leverage technology for better security and prevention and cure of disease. We're not just imagining this world. Our research is creating it, with you, for you.
We believe in you, the challenger, the visionary, the scholar. We believe in the contribution you make to our community, to our daily lives. We believe in the power you have to change minds, to change how things are done, to even change the world. Because we strive for those things too. At Unibank, we're determined to deliver better, smarter financial solutions to the university community, its students, staff and graduates. We'll take care of your banking so you can take care of the future. Unibank, no more.
Spiders are master chemists, and their venoms are extremely complex.
We get given the gene, then reproduce the protein to test on insect targets.
Can we use them for protecting crops, pesticide-free?
How does the world move forward? How do we progress to the next level? Through discoveries that set the wheels in motion. Through research that makes real progress. QUT research is harvesting the technology that can feed the planet, helping robots to see and learn, tapping into the power of big data, changing the way the body heals, and making real progress as we look at challenges through the lens of different disciplines.
Every challenge contains a seed of opportunity. Opportunities to improve life for all of us. We know this because we've been trusted to solve challenges for more than 100 years. We are proudly and uniquely placed to solve these great challenges through innovative science and technology to unlock a better future, better for our community, our economy, and our planet. CSIRO, Australia's national science agency.
Curiosity, collaboration, and courage to think outside the box are at the core of science and technology in defence. From developing high-tech capabilities to creating new technologies, defence researchers are at the forefront of our scientific advancement. We aim to inspire the next generation of scientists, researchers, and engineers. And our collaborative partnerships help solve some of our nation's biggest problems and protect our way of life.
Afternoon from the land of the Ngunnawal people, the traditional owners of the Canberra region. The Academy acknowledges and pays respect to the traditional owners and the elders past and present of all the lands on which we operate, live and work. They hold the memories, traditions, cultures and hopes of Aboriginal and Torres Strait Islander peoples of Australia. My name is Anna Maria Arabia and I'm the Chief Executive of the Australian Academy of Science. I'm delighted to be here today for another special event as part of Science at the Shine Dome 2021. As you know, Science at the Shine Dome is traditionally a 3-day event held in May where we gather at the wonderful, iconic Shine Dome in Canberra. This year, however, things look a little different and we're celebrating science online and reaching more people than ever before. So thank you for joining us wherever in the world you may be. We launched Science at the Shine Dome in May, and since then we have held our annual symposium and have celebrated many awardees. In November, we will also celebrate the Academy's newly elected fellows. All of the Science at the Shine Dome events are recorded, and they will be available on the Academy website 1 month after they go live. This afternoon, we're here to celebrate 5 of the Academy's awardees, the recipients of some of our career awards. We're delighted to be able to celebrate these awardees and we look forward to hearing from them soon. Before we get started, I'd like to make special mention of our event partners, all of which are on the screen and have made our online series possible. The contribution of our partners enables the Academy to continue to remain independent, foster and champion excellence, and make science available to everyone. So thank you. Your contribution is deeply, deeply valued. In particular today, I would like to acknowledge one of our major partners, the Queensland University of Technology. And to say a few words, we have QUT's Vice-Chancellor and recently elected Academy Fellow, Professor Margaret Shiel.
Hello, I'm Margaret Shiel, the Vice-Chancellor of Queensland University of Technology. It is a particular pleasure to be a part of the Career Awards events that both recognise the achievements of the awardees and the contributions of those for whom the awards are named. Together, these reflect the history, breadth and depth of Australian science. The inaugural Suzanne Cory Medal recognises one of our most outstanding contemporary scientists, and the Mawson Medal, one of our earliest scientific pioneers. I recorded this in a week where we celebrated the sporting success of our Olympians, which reinforces how important it is to celebrate the medals won by our many scientific stars. I congratulate all the award recipients, but especially QUT's Michael Bode, who won the 2020 Fenner Medal, and Christopher Dravandi, the 2021 Moran medalist. I'm also honoured to have been elected to join so many distinguished scientists in the Academy Fellowship this year. As a university with science and technology at its core, QUT is proud to partner with the Academy in supporting science at the Science Dome. This past year has demonstrated the importance of scientists and scientific collaboration within Australia and internationally, as we tackle the challenges not only of the pandemic, but the longer-term issues of the sustainability of our environment and society. These contributions have included those involved in modelling virus transmission, international collaborations on developing vaccines, and, for example, the work of QUT's and Academy Fellow Lydia Maraska in establishing the role of airborne transmission in the spread of viruses. Collectively, scientific expertise has never been in more demand as the public, politicians and the media seek explanations for data and scientific evidence. The Academy plays a crucial role in that through its promotion of science and strong public advocacy. In my case, my career transitioned from a practicing scientist to one where I have supported the careers and institutions that underpin our scientific endeavour. A different but equally rewarding journey. My scientific training in analysing problems, reviewing the data and managing and explaining difficult concepts and risks has been a huge advantage over the past 18 months as I have led the QUT community through the challenges of 2020 and 2021. I'm pleased though that QUT has been able to continue to support the next generation of scientists who will be so crucial to our future. Congratulations to everyone involved and good luck for today's event.
Thank you, Margaret, for QUT's support of science at the Science Dome, and congratulations on your recent election to the Academy. We will now start our presentations and question and answer session with our awardees. If you have a question for an awardee, please enter it into the Q&A section on the right-hand side of the portal. Now, to introduce our first awardee, please welcome Academy Vice President, Professor Malcolm Sandbridge.
Thank you, Anna Maria. I too am delighted to be here today, celebrating Academy awardees. In particular, I join you to celebrate the 2020 Haddon Forrester King Medal. The Haddon Forrester King Medal, sponsored by Rio Tinto, is one of the Australian Academy of Sciences prestigious career awards for lifelong achievement and outstanding contribution to science. The award is made in honour of the contributions of the late Haddon Forrester King, whose work applied the geological and related sciences to the search for mineral deposits in Australia and elsewhere. It recognises original and sustained contributions to earth and related sciences of particular relevance to the discovery, evaluation and exploitation of mineral deposits, including the hydrocarbons. And in 2020, this medal is awarded to Professor Ian Campbell. Before we hear from Ian, I will read his official citation. Professor Ian Campbell is widely recognised internationally as one of the world's leading experts in ore deposit geology. After graduating from the University of Western Australia, he spent 3 years working for Western Mining Corporation at Canberra, where he found the Wan Chute, one of the richest nickel deposits in Western Australia. He's had a long and distinguished career in mineral exploration and research relating to the origin of magmatic sulfide deposits, particularly platinum group element deposits and later porphyry copper deposits. His hypothesis for the origin of PGE deposits, i.e. platinum group element deposits, was initially controversial, but recent experiments have confirmed its key predictions. Several of his projects have been directed at discriminating between economically mineralized and barren bodies of rocks. The outcomes of these projects have direct application in exploration. Congratulations, Ian, and now to Ian's presentation.
Let me start by saying how humbled and honoured I feel to be awarded the Haddon Forrester King Medal. When I look at the list of those who have received this medal previously, it's a very impressive list of people who have made major advances in exploration for minerals and in mineral research, mineral deposit research. Some of the names that come to mind immediately are people like Roy Woodall, Dave Cook, David Groves, Tony Nordred, Neil Williams, and Steve Scott of the University of Toronto. After I finished my degree, my first job was with Western Mining, where my father was chief geologist. He also joined Western Mining immediately after getting his degree, and his boss was Haddon Forrester King. When he retired, he was replaced by Roy Woodall, who was a previous recipient of this medal. I was appointed at the ANU in 1985 to carry out fundamental research on the origin of ore deposits. And the aim was not to study the deposits themselves, but to study the environment in which the deposits formed using the existing techniques that were available at the ANU. And these included the iron probe, which had just been developed at the ANU, argon-argon dating, and these were used to determine the age of the host rocks to the deposits and the age of the deposits, and radiogenic isotopes to trace the source of the fluids that form the deposits. Most of this research was carried out by my 30-odd students. But during the course of their work, from time to time, they came up with fundamental problems that were not part of their research, or with new techniques which could be applied to other problems. And what I want to do is to give you one example, because this is the type of research that occupied much of my time. About 20 years ago, we started work on the giant Chuquicamata copper deposit in Chile. At about the same time, the Australian National University was developing the laser ICP-MS for measuring trace elements in minerals. The precision of the data that we were able to obtain exceeded our wildest expectations. So we decided to try to use it for dating zircons using the uranium-lead method. Zircons occur as a trace mineral in granites, and the advantage of zircon is that it takes uranium into the structure, but not lead. Any lead that is in the structure comes from the radioactive decay of uranium, so by measuring the uranium-lead ratio of zircons, we can date them. The first application of this work was to 3 granites or porphyries that are intimately associated with the ore at Chuquicamata and are thought to be the source of the mineralization. When we dated them, we expected that all of the ages would be the same, but in fact there was a 1 million year difference between the oldest and youngest age of the porphyries. The student who did this, Julian Ballard, was asked to do it again to make sure it was right, and he got the same result. In fact, he repeated it 3 times and continued to get the same result, which was later confirmed by shrimp iron probe dating. When we published this, it was the first high-precision dates produced by laser ICP-MS, and it showed for the first time that porphyry systems that produce giant ore deposits formed over an extended period of time. The advantage of the laser ICP-MS over the shrimp is that it's 10 times as fast, and dating can be done at about a tenth the cost. We can also measure trace elements in zircon at the same time that we do the dating, so it makes it ideal for the study of detrital zircons. Over a period of 20 years, we collected detrital zircons from the world's major rivers, and we dated them and analysed them for trace elements, including lutetium. Panel A shows the abundance of zircons of different age from 50 of the world's major rivers. The grey shaded areas are periods of supercontinent formation. Notice that the peaks in zircon formation coincide with the periods when supercontinents were forming by colliding together. When they collide together, they form mountains, as India is colliding with Asia today to produce the Himalayas. Below high mountains like the Himalayas, there are deep roots, and the roots go down about 5 times as far as the mountain goes up. When the mountains erode, they leave behind metamorphic belts, and the higher the grade of the metamorphic belt, the higher the mountain. Panel B shows the average metamorphic pressure of metamorphic rocks as a function of time. Notice that the peaks correlate with the peaks in zircon production, which in turn correlate with periods of supercontinent formation and mountain building. The higher the peak, the higher the mountain. So we can use the height of metamorphic peaks to make an estimate of the height of the mountains that were forming at the time. Notice at the bottom, towards the bottom of the diagram, the garnet inline. This is the pressure at which metamorphic garnet forms below mountains. Panel C shows the distribution of low lutetium zircons as a function of time. Lutetium is a heavy rare earth element that has a strong affinity for both zircon and garnet. Garnet starts to crystallize when the roots of the mountain exceed a pressure of 1.2 GPa, which is equivalent to a depth of about 40 kilometers. Once abundant garnet starts to crystallize in a rock, it sucks out the lutetium from zircon, which is present as only a trace mineral, resulting in low lutetium zircons. The higher the low lutetium peak, the more extensive the mountain range that eroded to produce the low lutetium zircons. As a consequence, we can use the height of metamorphic peaks to evaluate the height of mountains before erosion, and the abundance of low lutetium zircons to evaluate the extent of the mountain range. There are 2 peaks of low lutetium zircon production, and they were produced by erosion of the Nuna and Gondwana supermountains. They are unique in Earth history, and they had a dramatic impact on evolution. Rapid erosion of these supermountains produced a surge in the supply of essential nutrients such as iron and phosphorus into the oceans, which led to a bloom in primary production and to an explosion in evolution. The Nuna and Gondwana supermountains are associated with a 6 to 7 orders of magnitude increase in biovolume, the maximum size of species, and with the 2 most important steps in evolution. The Nuna supermountain correlates with the appearance of eukaryotes, the key building blocks for the evolution of plants and animals, and the Gondwana supermountain with the Cambrian explosion of animals. There are no low lutetium zircon peaks between Nuna and Gondwana, a period known as the Boring Billion, when evolution failed to progress. I am very honoured to be receiving the Haddon Forrester King Medal. Thank you for your attention.
Thank you so much, Professor Ian Campbell, for that presentation. It's now my pleasure to welcome Professor Ian Campbell live with us today.
Thank you.
And congratulations on receiving the 2020 Haddon Forrester King Medal. Ian, I have some questions for you, but I invite our audience members to also post some questions into the Q&A panel on the right-hand side of your screen, and I'd be very happy to ask those questions on your behalf. I'll start at the beginning, I guess. Ian, you mentioned your personal relationship to Haddon Forrester King, who was your father's boss when he was a chief geologist at Western Mining. Did your father share any impressions of working for Haddon Forrester King?
Not a great deal, but he was a legend, or he is a legend in the mining industry. And I spent a lot of time in Kalgoorlie in my early years. And in the back bar of the Palace Hotel, he was often talked about. Some of the science that he did really had a very big impact on how we think about how ore deposits form.
He does absolutely sound like a giant in the field. Because of the Academy's hosting or bestowing the Haddon Forrester Medal, I've had the opportunity to meet many members of the Haddon Forrester King family, and the stories are rich and wonderful. It must have been very special to have a personal connection. How special is it for you, Ian, to follow in your father's footsteps and now receive this medal in his boss's name?
Oh, that's a hard question to answer. We did very different things. He stayed entirely in the mining industry, and he wasn't very keen that I get into research. He felt that people doing research were wasting their time, that I should get a real job. And he insisted that he didn't insist, he encouraged me to work for mining companies for 3 years, but before I started my PhD.
Wow, that's interesting. And do you think that altered the course of your research eventually?
Yes, it did, because university people, for the most part, haven't worked in the real world, and they don't appreciate the importance of making a profit and making things work. And I think having had 3 years' experience working for mining companies has helped me understand what their problems are, what the sorts of results they want from research. And it's been useful to keep a foot in both camps, to know what mining companies are doing and also to know how research people view the world. And they're quite different.
An important perspective, and you're right, there is not an abundance of researchers who have had a foot in both doors, I guess. That's terrific. You mentioned, of course, that no area of research or research effort happens alone, and you shared a list of the names of your students who supported your research over the years. How did they inspire and help drive that effort forwards?
Well, all of the research, all of the students that I've had, or not all of them, most of them have done different things. And I found it very rewarding to work with students. Our students bring a very, very different perspective. They bring a fresh mind. And we often disagree on the interpretation of data. And I think that that's a very healthy thing. Having a good debate with a student is very worthwhile, both from the student's point of view and from my point of view. We both learn from each other. There was a professor at Berkeley called Ian Carmichael who said a good graduate student teaches his professor something new each week. And I've had a lot of very good research students.
What a wonderful saying. I think that's right. And that's the very creative space where new ideas are formed and new research endeavours are launched. That's terrific. Thank you too for acknowledging them. We know that our younger researchers really do hold up the nation in many respects in terms of being the arms and legs of the research effort. You talked about the technology used to research the origins of ore deposits. How did you see that develop over time? Were there directions that were really most surprising for you?
Well, there are two major changes during the time that I was at the ANU. The first was the development of the shrimp by Bill Constant and his group. And at the time that I arrived at the ANU, which was originally in 1983 when I went for 2 years, the shrimp was just starting to produce data, and that really changed the way we dated rocks, and it was a major step forward. And then the development of the laser ICP-MS, and that was done by a group of people at the ANU. The person who initiated it was Bob Laux, who recognized that if you changed the form of the laser that was being used, the way he did this was he went across to the physics department and he talked to them about what sort of laser should be used for analysis of silicate minerals. And he was told that we should be using an external laser, not the laser that we had been using. And by changing to that type of laser, we greatly improved the ablation that we were getting. And that improved the precision of the data by perhaps a factor of 1,000 or even 10,000. It was a huge improvement. And Steve Eggins, our previous director, was very closely involved in that. So that was a huge leap forward, and I was very fortunate to be there right from the beginning and to be able to take advantage of that.
Fascinating. Thank goodness for collaborations. I'll go on to the next question. Again, if our audience members wish to ask a question of Professor Ian Campbell, please pop that into the Q&A on your screen. Ian, your explanation for the origin of platinum group element deposits was initially very controversial. What did it take for that to be accepted? How did that turn around?
The thing that made it controversial was really looking at the origin of the Merensky Reef in South Africa, which is where most of the world's platinum comes from. And there were two hypotheses for the origin of the Merensky Reef. One was that it was hydrothermal, produced by fluids. The other was that it was magmatic and precipitated from a magma in a magma chamber. The second hypothesis required the partition coefficient between the sulfide that hosts the platinum and the melt to be about 1 million, whereas experimental work had suggested that it was less than 1,000. And I was convinced that the ore, and I wasn't the only one, but one of many who was convinced that the ore had to be magmatic, and therefore the partition coefficient had to be very much higher than people accepted. And together with Tony Nord and Steve Barnes, who's now at the CSIRO in Perth, we published a paper saying that the platinum group element partition coefficient was 1 million, not 1,000. And that was accepted by some people initially, but a lot of people didn't accept it. And it took 30 years before the measurements were made that proved that hypothesis right.
Absolutely extraordinary. Perseverance gets you everywhere. But we know that in science it often does take that level of verification. We do have a question from the Vice President of the Academy, Professor Malcolm Sandbridge. He says, great talk, Ian. Congratulations. Some young people seem to underestimate the importance of minerals to the future of the green economy. What do you tell your students as to why they should work on mineral exploration?
Well, there are two ways that we can answer that. One is, as a society, that is on a worldwide basis, we need minerals like iron ore, copper, any of the minerals that we mine. Without them, we wouldn't have the very high standard of living that we have. From an Australian perspective, I think it's something like 52%, and it might be higher now that the iron price is very high. But our major export by a long way, our first export is iron ore, our second export is coal, the third is gas. If you take those away, we wouldn't be the wealthy country that we are. So it's important to maintain our high standard of living, and it's also important to the wealth of our country.
Thank you. I'll turn to the geology of WA. It's known for being very flat, of course. Do we know how high the mountains were where those mineral deposits were formed that you spoke of during your presentation?
We can't give an absolute value on it. What we can say is that where the metamorphic pressure is highest, it had to have been buried under the largest mountain. So we can give a relative height, but we can't say the absolute height.
May I ask, over the course of your career, both in collaborations with the mining industry and in pursuing the research, was some of these questions, was Indigenous knowledge offered to help understand some of these historic questions? Was there knowledge that was able to be incorporated into your research from the Aboriginal and Torres Strait people of those lands that was useful?
I don't think the Aboriginals were very interested in mineral deposits, so the answer to that is no. They had no appreciation of gold. For example, a friend of mine, Jim Layler, was doing exploration in Western Australia, and he showed that the Aboriginal what copper looks like, or how it's found at the surface, and one of them brought back a sample with copper on one side. He turned it over, and there was a gold nugget on the other side. So gold had no value to them or to the South Americans before the Spanish got there.
Fascinating. There is a whole body of research to explore there, there's no doubt. And you mentioned the impact that the erosion of supermountains had on the evolution of life on Earth. What do you think Earth would look like had these mountains have never formed?
Well, there wouldn't be life on Earth as we know it. Most of the nutrients in the oceans come from the erosion of mountains, and the nutrients provide the bottom of the food chain. So they're essential to develop the primary production in the ocean, which is the start of all life. It becomes less important once you get plants on the continents. So from about 400 million years old, nutrients into the ocean become less important for sustaining life. But if you want to have fish, then you need nutrients going into the ocean, and they come very largely from mountains.
Fantastic, thank you. Moving to today and recent developments in ore deposit geology, what areas are you most interested in, or you keep a careful eye on still today?
Most of the work that I'm doing and my students are doing are in relation to porphyry copper deposits.
Okay.
And copper is essential if you want to have a green economy.
Which goes back to Malcolm's question, of course. We need all of those minerals to supply the things we've all become very accustomed to and will increasingly rely on going forward. Thank you. And where do you see your research heading in the future?
Well, we're going to continue to work on porphyry coppers. That's where most of the interest is, and research that we're doing at present involves applying platinum group element geochemistry to porphyry coppers, which has not been done before.
Mm-hmm. Thank you. I have one last question, but I will check that there are no more questions from the audience. If you'd like to post a question, please do so on the Q&A panel on the right-hand side of your screen, and I'm happy to pass that on to Ian. Whilst that's happening, if anybody wants to ask any further questions, Ian, what would you say, or what advice would you give to young researchers who may be watching today about a potential career such as the one you've followed?
Well, I think you've got to really love research. It's not a career that pays very well, but it's very rewarding. I get up every morning and I'm looking forward to going to work. I'm not sure too many people do that. I've been retired since the end of last year, and I'm probably working harder now than before I retired, and I'm enjoying it.
Yeah, that's great. They say it's no longer work when you don't experience it that way. So if you're enjoying it, you don't experience it as work. So what a terrific place to be in. Professor Ian Campbell, thank you. That's all we have time for. Congratulations once again on being the recipient of the Haddon Forrester King Medal. And we look forward to speaking with you again in the future.
Thank you very much.
Thank you. And now, to introduce our next awardee, please welcome back Professor Malcolm Sandbridge.
Thank you, Anna Maria. I'm delighted to be here again today. This time, I join you to celebrate the 2020 Mawson Medal. The Mawson Medal recognises outstanding contributions to earth science in Australia and commemorates the work of the late Sir Douglas Mawson, geologist and Antarctic explorer. The award is made to a scientist normally resident in Australia and whose work has relevance to Australia. And this year, the medal is awarded to Professor Alan Nutman. Before we hear from Alan, I will read his official citation. Professor Alan Nutman has made some fundamental discoveries concerning the evolution of early Earth through numerous field campaigns in arduous conditions. He has revolutionised our understanding of Greenland geology by applying necessary detailed geological mapping and applying necessary geochronological dating he performed using state-of-the-art geochronological techniques. He is considered to be one of the leaders in the understanding of early history of Earth. Professor Nutman has also made significant contributions to understanding of ancient rocks through many successful international collaborations. Congratulations, Alan. And now to Alan's presentation.
So hello everybody, my name's Alan Nutman, and I'm just giving a little bit of summary of some of the things I've been involved with over the years. I'd be particularly interested in processes on Earth in deep time, and particularly whether there was any plate tectonics in the very early Earth, or whether there was something completely different. This has all sorts of knock-on effects on even evolution of life on the planet. So what I'm going to do just in this very brief 5-slide presentation is to show you that when you look at this very ancient geological record, that basically almost 4 billion years ago, you still had features like horizontal tectonic thickening, bringing, for example, the mantle over the crust. You also, as we've just discovered over the last few years, you actually have even ultra-high pressure metamorphism preserved in very rare instances. These kind of features exclude vertical tectonics, some non-uniformitarian in process, but they definitely support some form of very ancient plate tectonics. So anyway, why is all of this so difficult to do? One reason is that you've got very little in the way of that geological record preserved. So you have got only about 1/millionth of those very old rocks are still surviving today. And then you've also got the problem that when you look at what's surviving there, it has been very messed up and mangled by younger tectonic events, collisional mountain building and so on and so forth, corrupting the vast majority of that very tiny record. So the place on Earth which actually has got some really wonderful things preserved is a place called Isuabili Inland Ice in Greenland, where you got an amazing inventory of extremely rare clues about the early Earth. So we're just going to look at a couple of those here. So in one particular place, you've got mantle rocks with subduction zone like geochemical and fabric features. And in these, we actually get very rare relics of ultra-high pressure metamorphism. So this ultra-high pressure metamorphism is something unique to the modern subduction scenario. It is not going to occur in any kind of vertical tectonics. So that's one example of evidence of some form of plate tectonics at the beginning of the geological record. You also have other cases, like you have examples of rocks which are actually from the uppermost mantle now lying and placed over the upper crust. And again, the places where this occurs are exceedingly rare, and probably the thing I'm showing in the picture now is the best place in the world to observe this, again in West Greenland. So we've got upper crustal rocks of altered basalts and some sedimentary rocks, and then these are overlain by upper mantle rocks. So the only real way of doing this is to actually push in a convergent compressional environment, push bits of a mantle over the top of the crust. So we can now move on and look at what these different scenarios have looked like. So really, when you look at this very ancient geological record, things like this so-called stagnant lid model, which is only a model, it just doesn't actually match what we see in this very ancient geological record. In fact, you can have a whole series of different scenarios of plate tectonic-like settings or variants in which you're going to get things like bringing mantle rocks over upper crustal rocks and having bits which have got very high pressure metamorphism incorporated into the crust. So there was certainly some form of plate tectonic-like horizontal regime already in place about 4 billion years ago. And it was actually this dynamic setting which was the home of already diverse life. And this is shown by the sole surviving example of 3,700 million-year-old stromatolites found in Issawa. So these are actually only known presently at one outcrop. They are, of course, very controversial. Any science of interest should be controversial. And there's still a lot of debate out there whether they should be generally accepted as life evidence. And finally, I would very much like to say thank you to colleagues I've worked with for many years. So Clark Friend, I've been working with him for 46 years. And Vicky Bennett from ANU, we've been working together for 32 years. So thank you very much for my time. And I'm looking forward to still working on the early Earth for the next few years to come.
Thank you ever so much, Professor Alan Nutman. It is now my pleasure to welcome Professor Alan Nutman live with us today. Welcome, Alan, and congratulations. Alan, I have some questions for you. As with the other speakers, I invite questions from the floor. If there are people who wish to ask questions who are online, please pop them into the Q&A section of the portal, and I'll ask them on your behalf.
Okay.
To get started, what's it like to visit Issawa in Greenland? It seems like a remarkable place. Might have a technical issue.
Yes, I can hear you.
Okay. Terrific. So my first question is, what's it like to visit Issawa in Greenland?
Oh, it's certainly a wonderful place. And I haven't been, shall we say, put off it. I've first started going to Greenland in 1974 at the tender age of 19. As a field assistant, and I hope to be continuing for a few more years yet.
I bet you've seen some changes over that time. It's fascinating. And what are the unique features of Issawa that have helped preserve the geological formations that have enabled your research?
Well, the key things about Issawa is it's this very small area in the world which just simply fortuitously has been less affected by later mountain building events and elsewhere. And in this way, some of the very early original features of the geology have not been modified by younger events. It's an entirely fortuitous thing. It's a sort of same principle where if, for example, you look at the place where a bushfire's gone through somewhere in Australia, just inexplicably, you'll just have maybe one house standing and all around it devastation. However, finding these areas of best preserved, very early geological record is a time-consuming thing. Although the world's oldest rocks are now only about 1/millionth of the crust, it is actually only a very small amount of that 1/millionth which can give you the clearest picture about very early processes, whether it be big things like the tectonic regime or the advancement of life in the early years of the planet.
Sounds absolutely fascinating. I'm interested in exploring plate tectonics a bit more. And why would the Earth not have plate tectonics? What are the alternatives?
Well, the alternatives are what are actually proposed on other waterless planets, where you have basically a stagnant crust, a stagnant lid, and actually it's the involvement in water and having a hydrosphere, which is a very, very important thing in driving plate tectonics and what goes on at the boundaries between where plates are converging. And in fact, one of Ian Campbell's very early contributions, paper in 1983, actually pointed out the great importance in water in controlling the tectonic regimes on Earth compared to our neighbouring planets.
It's difficult to imagine not having plate tectonics. It's an extraordinary relationship with the water hydrosphere, as you said. We have a question from our audience that relates to plate tectonics, and that's, what is your best estimate of when plate tectonics started, and would it have looked like the plate tectonics we see today?
Yes, well, there's a raging debate at the moment about when plate tectonics has started, and the, shall we say, the time frame for this actually varies according to who you talk to by more than 1,000 million years. There's also a real problem with semantics. Plate tectonics, some people want to regard plate tectonics as something exactly what is happening on Earth today in terms of the size of the plates, the length of the various plate boundaries, and so on and so forth. Whereas what we're most interested in is, shall we say, a mobile lid on the surface of the Earth as opposed to a stagnant lid. And that mobile lid regime would have had some similarity to modern plate tectonics, but some of the architecture of subduction zones and mountain belts could have been rather different. Semantics is confusing a lot of people in what you actually mean by plate tectonics.
Thank you. Has your research been stopped because of COVID-19? How critical is it to frequently visit places like Greenland and others to investigate these things?
Yeah, it hasn't really. Basically, at the moment, I'm sort of in a little bit of a gap between going to Greenland. We had a few very successful field seasons just before COVID hit, and in a way it means that I can sit here and actually clear some of a backlog of data by churning out some more publications, clearing the decks for hopefully going back into the field in time for my 50th year anniversary of going to Greenland.
Oh, wow. I hope there's a celebration in stall. Whilst we didn't want a pandemic, having some desk time to publish our research is a wonderful thing, to be fair. Another question for you, Alan. In your presentation, you said that 3,700 million year old stromatolites are controversial. Why is that? What makes them controversial?
Well, what makes them controversial is, to start with, they've only been located in only one place on the planet so far. And I think that's simply a matter of this obliteration by younger geological processes. At the moment, the evidence is based largely on the shape of the things and the fact that they have the kind of internal layering that one would expect within stromatolites. At the moment, one issue would be that you cannot see some of the details that you see in modern stromatolites, because these things have been metamorphosed up to about 500 degrees Celsius. And under that particular set of conditions, you get coarsening of the crystalline structures in any rocks, and this can lead to obliteration of some of the evidence. So there's it's certainly something which is very controversial at the moment. Basically, I think that anything of interest is never accepted or right away, and it's going to be a debate which will be playing out over the next 10 or 20 years, by which time I might be pushing up daisies anyway.
Look, you're absolutely right. We heard from some of our other awardees that very point, and we saw it with Einstein's work. It's taken 100 years for some of those things to be proven. So, look, all strength to you. I hope those controversies continue to be resolved over your lifetime and those of your students. Speaking of controversies, have there been others in your scientific career that are of particular interest?
Yeah, well, one particularly large controversy revolves around the use of the ANU's iron probe shrimps to date the oldest rocks in the world. For many years, I was actually part of the ANU shrimp group. I was there until 2006. I'm still a regular visit back there to do lab work. Basically, when we started to demonstrate that these very old rocks in Greenland were not just a simple uniform age, but in fact showed a very complicated history of crustal evolution over about 300 million years, it was not particularly well received by particularly a group in Oxford University, who themselves self-styled themselves as the Oxford Isotope Police. And again, this is something which has taken many years to resolve, but it is now, shall we say, just simply taken that when one looks at these very old complexes of rocks, that they don't just have bang one age for all of them, but when you start to dissect them, that you actually find very long, complicated histories of crustal development, which emulate very much what one sees in the construction of modern crust and modern mountain belts.
It's fantastic, thank you. And it does show us the richness of the research endeavour. Alan, how can understanding the history of the Earth's surface and beneath it help explain the evolution of life on Earth? And think about it from a layperson's perspective.
Yeah, well, I guess a very important contribution that the early life research by many people, including people who do a lot of work in the Pilbara region of Western Australia, it really shows the great antiquity of life. It shows that if you have a suitable planet with a retained hydrosphere, that life is actually going to evolve very, very early on. And when one actually looks at the evidence for oldest life on Earth, one is actually within the same time frame when Mars was still wet. And so this really does open up a great deal of hope that when people do finally get the right technology on Mars, that there will be found evidence of life, probably extinguished life. And I think that another interesting thing about the geological research is that there is parallel, of course, genetic modeling, which shows that LUCA, basically the last universal common organism, actually was somewhere around about 4,000 million years ago. So you've got these two completely unrelated branches of science coming up with the same answer, showing that life on Earth is extremely ancient. And also, as I said, importantly, that if you have a watery planet, that life is going to evolve and evolve very early.
So, Alan, are there tectonic plates in Mars, in Mars? It had water?
There's not really tectonic plates on Mars. There are highlands and lowlands. Basically, people can use the topography, very detailed topography of Mars, and flood it to show what areas might have been oceanic, and also, of course, the wonderful imagery that one can see. It does show rivers, and one does show some tectonic features, some so these very big rift zones and so on. In fact, I use imagery from Mars in some teaching, particularly with high school kids who are interested in coming to university and doing science, showing them the rivers on Mars and so on. And this is just readily available via Google Mars, which, of course, most kids haven't clicked on the icon at the top and realized that you got Google Mars, Google Earth, and Google Moon. So there isn't the evidence of the great level of tectonic activity that we see on Earth.
Well, they may have heard it here first, Google Mars and Google Moon. I must admit I hadn't noticed that either, so I'm going to have a look. And how inspirational for younger students who are thinking about not just a career in science, but thinking about geology, earth sciences, and the applications they'll have in their lifetime and beyond. It's so inspirational. Thank you for sharing those stories with us. I have a few more questions, but again, I invite audience members, if there are any questions coming in, please pop them into the Q&A section, and I'd be very happy to ask those of Professor Alan Nutman. I'll go on until then. Can you tell us more about the process of identifying the age of rocks? What kind of state-of-the-art geochronological techniques are you using?
Yeah, well, this was covered a little bit by Ian Campbell. The method used is zircon dating. As Ian Campbell pointed out, zircons are wonderful crystals. They're basically zirconium silicate, but they take in a range of trace elements, including uranium, but their lattice doesn't like to take in lead as they crystallize, and therefore if you like, the radioisotope clock is reset to zero every time you grow a zircon. And zircons are also a little bit like tree rings, in that you can have different growth zones within zircons, which relate to different geological events. So, for example, when we're looking at these very old rocks in Greenland, almost approaching 4,000 million years ago, one can actually get younger growth zones on the outside of the zircons, which relate to metamorphism and mountain building processes more than 1 billion years later. And all of this is possible by these microanalytical techniques like the big iron probes developed in ANU, where you're able to sample little areas on the zircons which are only sort of 20 microns across. And at that kind of spatial resolution, you can actually get the individual age of different growth zones rather than a geologically meaning average age for the whole crystal. So it is by the application of the uranium-led method, particularly by shrimp. But as Ian also pointed out, zircons are actually wondrous little beasts. They actually can provide a whole lot of other information. So, for example, the lutetium-hafnium system of zircons, they will actually tell you whether that particular igneous rock is, if you like, a new addition to the crust, or whether that igneous rock has been produced by the melting of significantly older crust. So that's the main technique. I've actually been doing zircon chronology for 33 years, in other words, exactly half of my life. And over that time, I guess I've accrued very large amounts of data, not only just in Greenland, but actually in collaborative projects from all around the world, not just on very old rocks, but also, for example, timescale related things in the Phanerozoic.
Thank you, Alan. I'm always so amazed by the breadth of the work and yet the very microscopic part of it. It really does cover it all. It's a fascinating area of study. I want to go back to your own personal interests. How did you first become interested in geology, and what do you enjoy about it? I'm sorry if I cut you off. I don't know.
Okay, yep. So it's actually a very interesting connecting story because I guess when I was about 16, you can probably gather by my accent, I grew up in England, although surprisingly, I was actually born in Canberra in the hospital that they blew up by the lake. But anyway, when I was about 16, I was having to sort of decide, what to do later on in my life. Geology was certainly something already of interest. I was also a bit interested in engineering. But then I remember seeing this documentary program on TV. It was called The Restless Earth, BBC production. And I had two images in that which I can still remember. One is somebody sitting very high up in some mountains somewhere, mapping geological structures. And interestingly, the other image was somebody who was to become my colleague for many years, a guy called Vic McGregor in Greenland, showing the remarkable discovery of very old rocks which had just been made. So actually that documentary really made me decide, yes, I want to become a geologist, and particularly a hard rock geologist. And then the university, which I did my undergraduate degree at, Exeter University in the UK, he basically at that university, they had a mapping contract with a Geological Survey of Greenland, and they took on undergraduate students as assistants in that program. So at the end of my first year at university at the tender age of 19, that's when I first ended up in Greenland. First field season was something like best part of 3 months long. One was dumped out into the field just with one geologist for the best part of 3 months. One basically worked around the camp, walked as far as one could doing the mapping, then the helicopter would come and move you about a week later to another spot, and so on and so forth for the best part of 3 months. So that's how I actually got into doing geology, and it's interesting that one of the first things which inspired me was actually a bit of Greenland research.
Professor Alan Nutman, it is such a pleasure to speak with you and hear about these things. It reminds me of the inspirational power of good science communication like the one you heard through the BBC. And I imagine at the time it would have just been a great big adventure to be camping and trekking through Greenland, collecting samples, mapping things out. It sounds absolutely wonderful and obviously a very formative time of your life. That's all we have time for today. I'd like to congratulate you again on receiving this award. It's richly deserved. Thank you for your time.
Okay, you're welcome. And I do feel, I guess, humbled by receiving such a reward.
Thank you, Professor Alan Nutman. Now to introduce our next awardee, please welcome Academy Fellow and Council Member, Professor Sue O'Reilly.
Thank you, Anna Maria. I too am delighted to be here today celebrating Academy awardees. In particular, I join you today to celebrate the 2021 Jaeger Medal. The Jaeger Medal is a career award made in honour of the contribution of the late Professor John Conrad Jaeger to Australian earth science. The award is made to a scientist for investigations of a high order into the solid earth or its oceans, carried out in Australia or having some connection with Australian earth science. And in 2021, this medal is awarded to Professor John Church. Before we hear from John, I will read his official citation. Professor John Church is one of Australia's leading oceanographers whose theoretical and observational work on the dynamics of the oceans has led to a deep understanding of the physics of recent sea level change, both globally and for the Australia-Pacific region. He has played a leading role in establishing a consistent and robust record of sea level change, integrating the traditional tide gauge records with satellite radar altimetry data, identifying its temporal as well as regional variability, developing a deep understanding of the processes driving this change, and providing quantitative projectors of future change under different climate scenarios that he has been able to test observationally. His work has contributed to the assessments of the science of climate change by the Intergovernmental Panel for Climate Change and to the World Climate Research Programme, and in the public debate on the evidence and the underlying science of climate change. Congratulations, John. And now to John's presentation.
Thank you. I've spent the last several decades studying how the ocean and sea level has changed in the instrumental and satellite era, and putting that in the context of the paleo record and also future projections. I work with sea level data measured by coastal tide gauges throughout the world. These measure sea level relative to the land at the coastline. I've also worked with satellite altimeter data, which measures sea level relative to the centre of the Earth. We need to recognise these are different reference frames. And of course, I've also been to sea many times, made observations and used global networks of in situ observations, and most recently observations from these profiling floats, which give us really good information on the upper 2,000 metres of the virtually global ocean. So what has contributed to sea level change? And can we balance it globally, regionally and locally? So there are many contributions: changes in mass of glaciers, changes in mass of ice sheets, not ice shelves, changes in the hydrological cycle, changing the amount of water stored on land, the extraction of water from aquifers and allowing that to run off into the ocean, and the building of dams storing water on land. And of course the ocean changes as well. As the oceans warm, sea levels rise, but not necessarily uniform. We can have changes in ocean circulation, both from anthropogenic climate change, but also as a result of natural climate variability, and that changes regional sea level rise. I've also addressed the question of why is sea level changing, what are the drivers of the change, what are the projections for the 21st century and beyond, and can we use observations to help narrow the uncertainties with those projections. So what have we learned? One of my first results was this estimate of global average sea level change from 1880 up to the present. This gave us a continuous time series of global mean sea level and clearly showed an acceleration from 1880 to the present. And the red line here is the satellite altimeter record, and as we will see later, that also shows an acceleration in the rate of sea level rise. Other people can do this probably better than we did back in the early 2000s, and we're just about to update our estimates to using some more sophisticated techniques. One of the major contributions to sea level rise is ocean warming. What's shown here is ocean heat content from 1950 up to the early 2000s. Ocean heat content is really important because in anthropogenic climate change, over 90% of the heat that's trapped in the climate system is in the ocean. About 3% goes into warming the land, 3% into melting the ice, and about 1% into warming the atmosphere. So understanding the ocean is really key. The historical observations we had in the early 2000s were shown by these red and yellow lines, and they had this large variability, decadal variability in the 1970s and 1980s, which no models could simulate. It turns out this is primarily an instrumental bias issue, and of course there are significant sampling issues associated with fewer observations in the Southern Hemisphere. So working with Katia Dominguez, one of my postdocs, we came up with this revised estimate shown by the black line with the uncertainty estimates. And when we compare that with global climate models for both ocean heat content change over the historical period and also thermal expansion, there's much greater similarity between both the trends in the signals and also the interannual variability in the signals. Larger signals driven by these volcanic eruptions of Pinatubo, El Chichon, and Mount Agung in the models, primarily because the observations are too coarse resolution to accurately depict the response of the ocean. One of my large focus has been on understanding the reasons for sea level change. Can we actually close the budget to the sum of these contributions equal to the observed change? This is one of our most recent results. It's in the final stages of review. So over 1958 through to 2015, the observed global mean sea level in the top panel in the center is about 1.8 millimeters per year. The sum of all the observations is just slightly less than that, 1.5, 1.6 millimeters per year. The largest contribution that's shown in red is the ocean thermal expansion, followed by contributions from glaciers shown in blue, and smaller contributions from ice sheets. But note this contribution from ice sheets, or in fact all of these contributions are accelerating, but particularly the contributions from the ice sheets. And there's a small negative contribution from changes in water stored on land. All of these signals have a spatial signature. So the ocean thermal expansion, the result of increased heat in the ocean, as well as changing winds, changing circulation, is shown in the top right-hand panel. So it's quite a complex panel with natural climate variability and anthropogenic climate change in it. For things like glaciers, so in regions near glacier loss mass, like up here in Alaska, sea level right near the region of glacier mass loss falls as a result of a change in loading of the Earth and change in the gravitational field of the Earth, and rises more than the global average in the far field. Similarly, for the other mass contributions from ice sheets and water stored on land. So we add all of those components together. We get the bottom right-hand column, including the ongoing motion of the Earth, and the coloured dots are coastal tide gauges. So it turns out that when you do a careful comparison of these in situ observations together with our sum of contributions, there's actually quite good agreement with very little bias averaged over the number of tide gauges we have. But what drives this signal? So you can do experiments with climate models, and this panel on the left now shows a range of different climate models, with the black showing the ensemble average. So prior to 1950, we explained about 25% of the observed rise. But after 1950, that rises rapidly, reaching about 70% in 1970 and stays about 70%. So we don't fully explain all 100% of the historical observed rise, but it's dominated by greenhouse gas forcing. And some of the missing components is associated with our interference with the water cycle in storage of water on land, and more recently, greater extraction of groundwater from aquifers. I've been lucky enough to be involved with been responsible for two sets of projections in sea level change for the 21st century, both in 2001, and 2013. And what I've shown here is the most recent set of sea level projections, just released in August this year. Depending on the greenhouse gas scenario, from a strong mitigation scenario here, such as SSP1, up to virtually unmitigated emissions, then the range of sea level projections to 2100 is roughly a half a metre to 1 metre compared to 1900. This is very similar actually to what we had in the last report, the AR5, in 2014, but about 10 centimetres higher, principally because of a larger Antarctic contribution. But we need to recognise there's a risk of higher sea levels, and the uncertainties associated with these projections are essentially one-sided. We can have substantially larger and faster rates of sea level rise than in the projections, but not substantially lower. In the AR5, we allowed about 0.6 of a metre for this additional contribution from Antarctica. They've been more explicit in the most recent report, as shown by this dotted line here, rising up to about 1.7 metres in 2100 and continuing. We should note that in the last decades of the 21st century, the rate of sea level rise in these scenarios, the high emission scenarios, is large. It's about equivalent to the last major deglaciation of the Earth, when sea level rose at over a metre per century for many thousands of years. So on the high emissions over centuries, we're talking about metres, many metres of sea level rise. Of course, there's a regional pattern associated with these projections, and shown here is 4 different climate change scenarios and the associated sea level patterns, from low emissions on the top left to high emissions on the bottom right. But it turns out that when you look at where the people live away from the polar regions, then most of the coastline experience a sea level rise within about 20% of the global mean rise. So much of the science, of course, is done in developing the models and comparing them with historical observations. But can we attempt to evaluate the projections themselves? So that's what we've done here. The projections from the last report are shown by the green and black lines in the top panel, and the historical observations shown by the various blue lines and the satellite altimeter by the red lines. It turns out that the projections are or the observations and the projections are in very good agreement. You cannot differentiate between the projections in terms of the mean rise over this relatively short period. But when you look at the accelerations, which lead to larger rises in the high sea level scenario, high greenhouse gas scenarios, these accelerations are already baked into the projections, and it turns out that the central value of the observations, although there's a wide uncertainty range, seem to be closer to the higher emission scenarios than the low mitigation scenarios. And the new direction we're attempting to pursue at the moment is, can we use observations to directly constrain future projections? So shown here is observations of near global ocean heat content over the period 2005 to 2019, when we have very good records, compared with global ocean heat content changes by 2100, and on the right panel, ocean thermal expansion by 2100. And all the symbols are various climate models, with the colour indicating the climate sensitivity of that model. So we notice that some high climate sensitivity models are well above the historical projections, and there are some simulations which are somewhat below the projections. So we can use these observations to help constrain and narrow the projections of ocean thermal expansion for the 21st century, and when they're working on extending that to other parameters from glaciers and ice sheets, etc. So I should stop there. Just thank all my collaborators, postdocs, students, collaborators both within Australia and internationally, and of course my family and other supporters. Thank you.
Thank you, Professor John Church, for that absolutely fascinating presentation. It's now my pleasure to welcome you live with us on being a recipient of the 2021 Jaeger Medal.
Thank you very much, Anna Maria, and I should say what an honour it is to have been awarded this medal, particularly when I look at past winners, and just to be listed on the same page is really such an honour. Thank you.
It's so thoroughly deserved, John. I know as a staff member of the Australian Academy of Science how much myself and my colleagues rely on you and your extraordinary research to help inform many of our much of our work and our reports. So thank you, and they were very neatly summarised in your presentation. I invite the members of the audience to ask questions by putting in questions in the Q&A on the right-hand side of your portal, and I'd be very happy to relay those to Professor John Church. I'll get us started though, John. How does the extraordinary work you've done on sea level rise help contribute to assessments made by the Intergovernmental Panel on Climate Change?
So the assessments really take in all of the work around the world. So if you look at the reference list in each of the chapters, then there are many hundreds of publications referred to. And yes, I've been pleased at some of my contributions, particularly the early records of the rate of sea level rise during the 20th century, its acceleration, and also the explanation for the rise by comparing the different contributions to the observed rise. And the attribution have been well referenced in these reports, and I think have made a significant contribution. Still, there's major challenges ahead, particularly in understanding what the ice sheet contributions are going to be to 2100 and beyond.
Thank you. And there is much to know, but your presentation illustrated to us that the predictions and the observations are very much in line, and that's encouraging. I think you also mentioned that our predictions going forward are on the conservative side. If anything, it would be worse rather than a better scenario. Could you, in simple terms, for people listening today who may not be scientists, what are some of the more worrying impacts of sea level rise since 1900, and what will be the experience in years to come, as far as you can tell?
Yeah, so there's a couple of different impacts. Firstly, coastal flooding events. We have about 100 million people living within a metre of high tide level at the moment. And so as you raise sea levels, you increase the frequency of coastal flooding events, and that can be quite dramatic. So we've already seen in the 20th century that the frequency of high sea level events that occur perhaps once a decade or once every 100 years has already increased by a factor of 3 on both the east coast and the west coast of Australia. And this has been observed elsewhere around the world. There's been quite a focus in the US on what is called nuisance flooding events, where roads get flooded, communities get cut off for periods. This impact increases quite dramatically as sea level rises. So by 2100, what is currently a 1 in 100-year event could be happening several times a year. So this will have significant impacts on coastal societies. And the other impact is, or perhaps I should add there, this is not just at the coast, but up estuarine areas. So the larger populations living right near estuaries that will also be subject to this type of increased flooding. And the other impact, of course, is coastal erosion. We see beaches eroding around the world now, and that will only increase as sea levels rise further during the 21st century.
Thank you, John. We have a question from the audience, from Ron Eckers, Fellow of the Australian Academy of Science. Do we expect future improvements in observational technology?
So the biggest improvement we've had recently is satellite altimeters. They've really given us a global picture of sea level, as distinct from the few records we had from coastal tide gauges during the 20th century. That satellite record is continuing to grow, and it's becoming increasingly valuable as it lengthens. There is a new generation of satellites that we expect, and that is giving us a much higher resolution, allowing us to get satellite observations right next to the coast. So that's an improvement that's coming. We've also had dramatic improvements in our ability to observe the ocean. So over the last 15 years, we've had floats that have profiled the upper 2,000 metres of the ocean, virtually globally. And this has really, for the first time, allowed us to estimate ocean heat uptakes much more accurately than sparse historical observations from research ships and merchant ships. We expect that over the coming decade, that will be extended to the full depth ocean rather than just the upper 2,000 metres of the ocean. And at the moment, we're missing observations from these profiling floats in polar areas, under sea ice, for example. And we expect that to change in coming decades too. And finally, we also now measuring from satellites gravitational changes of the Earth. And this equates to transferring mass from the land, from the ice sheets, for example, into the oceans. And we can start to measure that And again, we're getting a much longer time series of that. So there has been a revolution, and we expect that revolution to continue, particularly with more accurate and more localized measurements from satellites.
And I presume all that will lead to more accurate observations and modelling. To gather that information, that's obviously a global effort. You would be involved in many international collaborations. Who are your main collaborators who you rely on most or work with most? And I acknowledge that if you consider the authors of the IPCC reports, I mean, there's hundreds of people, but for your work, which key parts of the world do you rely on?
Yes, you're right. There are many collaborators. So recently I've relied very much on the people who provide the Argo observations of the upper 2,000 metres of the ocean. Of course, I also use satellite data, so we rely on that satellite community. But I think my closest international collaborator and a great colleague is Professor Jonathan Gregory from the University of Reading in the UK. He was a co-convening lead author of the third assessment report in 2001 with me, and he was also on the team in the fifth assessment report. So in my mind, he's perhaps one of the best sea level people in the world and one of the best climate research scientists in the world as well. So it's really been a pleasure to work with him, with his team and with his students, and I hope to be able to continue that into the future. But as you say, there are many collaborators in this field. Climate science is very much an international science. No single nation can do all the work that's required on their own.
Indeed, and not just international, but multidisciplinary. There are many, many disciplines required to complete the climate science picture. And John, I'll move on to the next question. You mentioned that greenhouse gas emissions are the biggest contributor to sea level rise, and you showed some projections of the future depending on action taken. How confident are you that we can slow the rate of sea level rise?
I'm confident we could slow the rate. I think we actually have the technology, and we will have new technologies into the future that will allow us to slow the rate. But what is lacking, actually, at the moment, is the will to try and do that. We see that occurring in Australian government's lack of commitment to emission reductions, and that's occurring elsewhere around the world. What's missing really is a recognition of the urgency of this issue. If we don't really cut our emissions drastically in the next few decades, we will cross thresholds that will commit the world to meters of sea level rise over coming centuries. We won't have meters this century, but we will have the conditions that might make that inevitable unless we act much more decisively than we have today.
So in short, it's avoidable today if we act, but in the future there may be a scenario where it's not avoidable. Of course, we have an important opportunity coming up in Glasgow through the COP26 meeting, where national leaders will come together and recommit and hopefully improve their global commitments to reducing greenhouse gas emissions in their respective countries. And we all not just hope, but very much encourage them to be guided by the science in their deliberations. This is a particularly important meeting. They're all important, but this feels particularly important given the urgency you've just expressed. John, I'd like to ask a bit.
Yes, might I just add? Just wanted to add in response to your comment there. Yes, we can prevent the worst case scenarios. We cannot prevent all sea level rise or all climate change. We will have to adapt. We need to recognise that and start planning for that as well as the mitigation.
Yeah, and we're a smart bunch. We have the wherewithal to do it. We just need to get on and do it. Thanks, John. I'd like to ask a bit about the development of your work since the first results you published in 2006. How difficult was it to come up with with a way to graph the acceleration of sea level rise during the 20th century. What sort of techniques have allowed that progression?
So the crucial issue was the combination of the short satellite altimeter record, which started basically in the start of 1993 up to the present. So it's a very short record, but it's global. And in comparison with that, we had the longer tide gauge records up to perhaps 200 years at maximum, but the very sparse distribution, and predominantly, of course, in the Northern Hemisphere in the early period. So coming up with that method to combine those was quite challenging. And our first paper on acceleration, I think we've been described as courageous, our comment that sea level was accelerating. So I guess it was pretty controversial then. People hadn't accepted the idea that during the 20th century sea level was accelerating. And similarly in the satellite altimeter record, there was actually small biases we identified, or particularly my colleague Chris Watson identified, in the early part of the satellite record, which masked what was an acceleration in sea level since 1993. Once we identified those biases, people have really jumped on the bandwagon now, and there's many estimates of the acceleration from the satellite record, most of which are larger than what we initially estimated. So it has been challenging, and it brings together many different disciplines, as you said earlier. People who understand satellites and how they orbit around the Earth, how the gravitational field changes, how the ice sheets are changing. So yes, it has been a challenge.
Thank you, John. We have a question from our audience from Professor Suzanne Cory. Thank you for being with us today, Suzanne. Suzanne asks, thank you for your talk, John. Have scenarios been published about the impact of sea level rise on the world's biggest coastal cities like New York and London, and also Australian cities? This would surely promote a sense of urgency.
There are studies done on many of these cities. So New York in particular, they had particular problems a few years ago with a major cyclone, or typhoon as they call it. So these places do have major plans for, well, how are we going to adapt to rising sea levels? For London, for example, we have the Thames barrier. Similarly in Netherlands, they have barriers which can be closed to storm surges. And in New York, they are planning what's called the Big U, which is around the southern part of Long Island, building barriers to protect that low-lying part of New York. So there are some studies done. There's some studies done in Australia, but less for the major capital cities and some of the more vulnerable regions. And the other issue for Australia is the eroding coastline, and that requires quite a bit more study, I believe.
Thank you, John. We're running out of time, so I have one last question for you, and that goes to the future. Where would you like to take your research in the future?
So we're trying to presently constrain projections. So in fact, we just had a paper come out today in Nature Climate Change where we were constraining estimates of ocean thermal expansion. But the real issue is what's going to happen to the glaciers, to the ice sheets of Antarctica in particular, to a lesser extent to Greenland. It's more understandable. I'm not a glaciologist, so I won't directly contribute to that, but I hope to try and incorporate those projections and also try and help constrain ocean conditions, which are a big control on ice sheet contributions to narrow our uncertainties of sea level change, particularly beyond 2100, where there's much larger rises and much more uncertainty.
Thank you, John, and all strength to you for those future endeavours. Thank you so much for your contribution to date. I'm sure there will be many, many deep and meaningful contributions coming forward as you go forward with your research with your teams, both here in Australia and across the world. And again, congratulations on being the recipient of the Jaeger medal.
Thank you, Anna Maria.
Now to introduce our next awardee, please welcome Academy Vice President, Professor Helene Marsh.
Thank you, Anna Maria. I too am delighted to be here today celebrating Academy awardees. In particular, I join you today to celebrate the inaugural Suzanne Cory Medal. The Suzanne Cory Medal is a career award that recognises outstanding research in the biological sciences. It honours the wonderful contributions made to science by Professor Suzanne Cory, who, as a molecular biologist, has made major contributions to understanding the genetic causes of cancer. And in 2021, this medal is awarded to both Suzanne von Caemmerer and Professor John Endler. We'll hear from John a little later, but now we recognise Suzanne. Before we hear from her, I'll read her official citation. Professor van Caemmerer is the preeminent authority on modelling metabolic, physiological, structural and environmental aspects underpinning photosynthetic carbon dioxide fixation in plant leaves. She changed the way we think about photosynthesis and gas exchange in leaves and remains at the forefront of this research. Her ability to combine mathematical modelling with experimental approaches and her progressive exploitation of ever more powerful molecular engineering methods throughout an outstanding career have refined and deepened our understanding of biochemical, physiological and environmental limitations to photosynthesis. Her research from leaf chorioplasts to global models of plant production aimed at enhancing photosynthetic rates in crop plants to increase their yields and adapt to climate change is now applied worldwide. Congratulations, Suzanne, and now we look forward to your presentation. Thank you.
I'm delighted to receive the Suzanne Cory Medal. Suzanne Cory is a past president of the Australian Academy of Science, and she was the first woman to be elected to this position. She was the director of the Walter Eliza Hall Institute of Medical Research, and she has made major contributions to understanding the genetic cause of cancer. Suzanne is a role model to us all. My talk will be about mathematical models of photosynthesis, but before I start, I wanted to tell you a little bit about myself. I came to Australia in the early 70s and I studied pure mathematics at ANU. I had been invited to come for a gap year by my aunt and uncle, Hannah and Bernard Nutman, and both fellows of this academy. And I stayed and finished my undergraduate studies here. And after that, I had the opportunity to start a PhD with Graham Farquhar, and this started my biological science journey, designing mathematical models of photosynthesis. As you know, photosynthesis is a process by which plants capture sunlight and convert CO2 and water into sugars and generate oxygen. This is the basis of all life on Earth. For photosynthesis to occur, CO2 has to diffuse into leaves through stomatal pores on the leaf surface shown to the left. At the same time, oxygen and water vapor diffuse out. It's now routine to use infrared gas analysis to accurately measure CO2 uptake and water loss from leaves under different environmental conditions. And an example of a portable system is shown to the right, where the system is clamped onto a tobacco leaf. I was lucky to be part of a team to present the first comprehensive mathematical model that related gas exchange to the underlying biochemistry of photosynthesis. The C3 photosynthetic pathway is the most common biochemistry of photosynthesis, and it happens within chloroplasts. The cycle on the right is where CO2 is fixed by the enzyme rubisco to make sugars. Rubisco is a large enzyme and a very slow catalyst, and it's probably the most abundant protein on Earth. The chemical energy required to drive this biochemistry is generated from absorbed light in the chloroplast electron transport chain, which is shown on the left. I will give you just a very brief description of our model. I have shown here a typical response of CO2 uptake to increasing CO2 concentrations. The data points are from gas exchange measurements made on a tobacco leaf. And although the biochemistry of photosynthesis is very complex with many enzymatic steps, we showed that CO2 uptake of leaves could be related to the amount of rubisco present in the leaves and its kinetic properties and the capacity of the electron transport chain to regenerate IBP. A rubisco limitation to photosynthesis occurs at low CO2 concentrations, and electron transport capacity becomes limiting at higher CO2 concentrations. The two basic equations are shown at the right and in the figure by the dashed and dotted lines. And the solid line shows the predicted CO2 uptake, hence photosynthesis. For the last 40 years, the simplicity of these equations has allowed people to use gas exchange measurements of CO2 response curves to quantify photosynthetic biochemistry in many species all around the world. And this means that these equations have also been embedded in canopy photosynthesis models and in Earth system models. Plants use different biochemistry for CO2 fixation. So far, I've talked about the C3 photosynthetic pathway, which happens in chloroplasts and in mesophyll cells, and shown here together with a cross-section of a rice leaf at the top. Two-cell C4 photosynthesis requires a spatial separation of fixation of atmospheric CO2 into 4 carbon acids by PEP carboxylase, and hence the name C4 photosynthesis, and the donation of that CO2 from these C4 acids to rubisco in the bundle sheath cells. This concentrates CO2 in the bundle sheath, helping to speed up rubisco carboxylation. A leaf cross-section of a sorghum leaf is shown at the right, and you can see what different leaf anatomy is required to run this pathway. C4 photosynthesis was discovered in the mid-60s by Hal Hatch and Roger Slack. Hal Hatch is, of course, also a member of this academy. Important crops like maize, sorghum, and sugarcane, and tropical grasses and many weeds use this pathway. And although floristically only 4% of species use the C4 photosynthesis, large tropical grasslands mean that about 25% of terrestrial CO2 uptake is fixed by C4 species. Our mathematical model of C4 photosynthesis also relates CO2 uptake to the underlying biochemistry. And here, a typical CO2 response of C4 photosynthesis is compared to that of C3 photosynthesis. Our model now predicts that rubisco and electron transport capacity limit the CO2 saturated rate of CO2 uptake, whereas PEP carboxylase limits the initial slope of the curves. And it's perhaps interesting to note that the model C4 leaf has a third of the amount of rubisco protein compared to the C3 leaf and achieves much greater photosynthetic rates. Proteins are nitrogen rich, and it's one of the reasons why many C4 species are far more nitrogen use efficient than C3 species. C4 leaves also have very high photosynthetic rates at low intercellular CO2, which means they can close stomata and conserve water, making them also more water use efficient. A lot of my recent research has focused on understanding and manipulating C4 photosynthesis, and I'm a member of the C4 Rice Consortium, which is funded by the Bill and Melinda Gates Foundation, and we are trying to insert the C4 photosynthetic pathway into rice to improve yield. In order to feed a projected 9 billion people by 2050, farmers will need to grow at least 50% more food on a limited amount of arable land. And increasing photosynthesis is now seen as one possible solution to help that, and we've been working to develop strategies on how to do this. I'm a member of 2 international consortia funded by the Bill and Melinda Gates Foundation. The first is called Realizing Increased Photosynthetic Efficiency, and it's an international research project that's engineering C3 photosynthesis. And the aim is to provide smallholder farmers in Africa with higher yielding crops. I've already mentioned the C4 Rice Consortium. We were also fortunate to be funded by the ARC for a Centre of Excellence on Translational Photosynthesis. I have only been able to give you a brief snapshot of the research that I'm involved with, but all of my research has primarily focused at the leaf level, trying to understand the photosynthetic mechanism. And I'm very pleased that that has provided information for canopy and global modeling of CO2 exchange, and is now helping to design and create new crops with improved photosynthesis. Research rarely happens in isolation, and I want to conclude by acknowledging my colleagues and collaborators. I particularly want to thank Barry Osmond for his guidance and mentorship all throughout my career. I was very lucky to be able to work with Graham Farquhar and Joe Berry on the C3 model of photosynthesis. And I was also very lucky and fortunate to have wonderful colleagues at ANU, including John Andrews, Murray Badger, Dean Price, and John Evans. And Bob Furbank and I have been long-term collaborators on all things C4 photosynthesis. Thank you very much.
Thank you for joining us, Suzanne, and congratulations on receiving the prestigious 2021 Susan Cory Medal. Suzanne, I have some questions for you. I just have a bit of an echo in my earplugs, so I'm sure that will be resolved. My first question to you, and of course I invite audience members to submit their questions in the Q&A section of the online portal. You started your presentation talking about how Suzanne Cory was inspirational to you. What does receiving the inaugural award in her name mean to you personally?
I'm very thrilled by it. Suzanne Cory is such a role model to us as scientists, but also to female scientists. When I started, thinking about doing science and going to university and so on, I was always told that it wasn't really possible to have a science career and raise a family and so on. So it's really nice to have role models now in society that show us that we can do science and have families and so on.
Absolutely. And may I suggest that you're one of those role models as well. Two great Suzannes, one a recipient of the award, but two extraordinary contributors to science. So thank you. Your career shift from pure mathematics to working on modelling photosynthesis is very interesting. Can you tell us a little about how that happened? How did you kind of swap disciplines?
Well, it's a little bit embarrassing. I finished my undergraduates in pure mathematics at ANU and I was on a student visa. And then I wanted to stay in Australia, and so I needed another visa. And the immigration department said that if I could find a job, they would give me a permanent residency. And luckily, Research Growthology was advertising technical officer positions, which at the time were all permanent positions. And that's how I started. I got to work with Graham Farquhar in the lab as a technical officer and then changed over to doing a PhD.
Absolutely fascinating, and a bit of serendipity in there, in the right place at the right time, or perhaps caught between the right visa.
Yeah.
Suzanne, we have a question from the audience from Professor Andrew Holmes, another former president of the Academy of Science. He says, excellent talk, thank you. Is it reasonable to argue that there has not been a Darwinian pressure on plants to improve photosynthetic efficiency?
Yes, I think actually what one has to realize is that plants out in nature have completely different problems to crop species that we grow in, certain configurations and so on. So I don't think there has been the pressure on increasing photosynthesis in the natural environment. And it's not that easy to breed for increased photosynthesis, so not that much has been done. But we do know that increasing photosynthesis actually does increase biomass and yield, because there's by now been lots of experiments done in phase experiments, which are open free-air CO2 enrichment experiments. So if plants are provided with more CO2, they're photosynthesized more, and we know that provides more yield. So we think it's a really good target.
Thank you. Just going back to some of the basics on photosynthesis, can you give us some insight into how difficult it was to come up with models for photosynthesis?
Well, I guess when I started, the problem really was we could suddenly make measurements of CO2 uptake, and so we could actually really make very precise measurements of photosynthesis. And I was trying to relate that to the biochemistry in the leaf. And as you know, the biochemistry is very complex. So it's really making the decisions of what to include into the models and what to leave out. And, there were some other models before us that had made, similar attempts. And I guess to some extent, we refined that and focused onto rubisco and its kinetics and also the electron transport capacity.
Yeah, and did you discover some beautiful mathematical structures while you were investigating those models?
Well, the mathematics is actually very simple, and I guess that's why it's been so successful. You can almost do it with a pencil and paper, do the calculations, and I think that's why it's been easy to incorporate in other models.
Yeah, fantastic. Thank you, Suzanne. You mentioned your work in helping to research ways to improve crop yield, which is critical to today and to our future globally. Can you tell us a bit more about how your models help achieve that? Give me a sense of context there. I know there's great interest from the board.
Yeah, so we have these basic models, and so we can use the models to have a look at and see what sort of enzymes we think we should perhaps increase the activity of and how we could perhaps enhance photosynthesis. And that's been really useful. We have a number of targets, and we've sort of developed them from looking at the models and see what they would predict. We can tweak the models and say, what would happen if we have a little bit more of this enzyme or that enzyme? And so the models have guided our sort of ideas of what we should do to enhance photosynthesis. And we've been successful in several instances, which is really pleasing.
Suzanne von Caemmerer, we have a question from Suzanne Cory. Congratulations, Suzanne, and thank you for your talk. Being juxtaposed to John Church's talk today makes me want to ask about plants and crops. Ask what plants and crops make the most difference in reducing CO2 levels and whether we can amplify that even more.
I think C4 crops are very good. They have very high activities and certainly have very high photosynthetic rates. But I guess our focus has really been to provide food for farmers to grow plants that have crops that have better yields. For reducing CO2, atmospheric CO2, of course, the forests around the world do an absolutely fantastic job. And I guess one of the really critical things that one doesn't want to happen is the warming of the sort of Arctic or cooler climates where the respiratory processes will be enhanced, which then release the CO2.
Thank you. Is it fair to say that without mathematical models to help improve crop yield, it would be significantly harder to achieve feeding the world's population of 9 billion by 2050?
Yeah, well, lots of things contribute, but certainly it's nice to be able to test ideas out before one actually goes and generates transgenic plants with variations and so on. So it's always a backwards and forwards of trying something and then seeing, can we understand the mechanisms of that, what we've just done and so on.
Suzanne, we know the Bill and Melinda Gates Foundation have been critical in identifying key global challenges and bringing together collaborators and consortia around the world to tackle those. You're part of the C4 consortium. Tell me a little bit about how you got involved in that and how that intense research effort is really helping move things forward.
Yeah, so a colleague of mine, John Sheehy, who was working at the International Rice Research Institute, wanted to try putting C4 photosynthesis into rice. And so he invited a number of us to come to Erie. And under the condition that we provided a chapter to a book on how to do C4 in rice. And so we all went there and we wrote a book and Erie published it. And then he went around the funding agencies to see whether anybody would be interested in funding the research. And it turned out that the Bill and Melinda Gates Foundation was up for it. I mean, it was a really pie-in-the-sky research idea, and we were very pleased to have it funded.
And has it made a difference to have them behind you and that global backing? I know they often contribute to many collaborators and really intensify the research effort. Has it really accelerated it in ways you wouldn't have expected?
It has really accelerated in the way we've been able to do research. I mean, we're an international consortium with different several nodes. We've so far had 10 years of continuous funding, and that is already something quite unusual. And we just yet received another 5 years of funding. So being able to do this very basic pie-in-the-sky research with consistent funding has been fantastic. The problem's been far more difficult than we thought. We sort of thought it would be easy to do it because C4 photosynthesis has evolved independently about over 60 times. And all the genes needed for the photosynthetic pathway, C4 photosynthetic pathway, are already present in C3 species. So we thought, how hard could it be? We should just be able to find the switches and so on. But it's not been very easy.
Yeah, famous last questions.
Yeah.
How hard could it possibly be in science? Yeah. Oh, okay, Haddon, I'm really pleased you had the additional 5 years of funding, and it is testament to the foundation to back that sort of research continuously. It does make a difference. Could I go to future directions? Are there any new directions you're keen to take your research in, or what are the next steps in your current research?
I guess I would be, I started off doing very basic research, building the models, and then, worked on other aspects like, how the CO2 diffusion inside leaves work and so on. And this seemed really basic research. So I guess I'm really thrilled that it actually seems to have some application and purpose. So I guess for the next 2 years, I'm very much focused to see whether we can get the C4 rice project to a conclusion, and also whether we can provide better crops for Africa. Yeah.
Thank you. And a question, inspiration, what would you say to a young person considering studying mathematics and the direction it can take them in the future?
Yeah, I guess it's important to have an open mind. And I guess the most important thing is to really enjoy doing it, because I think that's really the most important thing. You have to be able to want to do it.
Absolutely. And collaborations and teamwork is something very special about science that I think is often underestimated, as well as its global collaboration and reach. Professor Suzanne von Caemmerer, congratulations again on receiving the prestigious Suzanne Cory Medal. It is a pleasure to speak with you, and all strength to you in the continuation of your research. We hope to speak with you again soon.
Okay, thank you.
And now to introduce our next awardee, please welcome back Professor Helene Marsh.
Thank you, Anna Maria. I'm also delighted to celebrate the other recipient of the inaugural Suzanne Cory Medal, a career award that recognises outstanding research in the biological sciences. It also honours the outstanding contributions of Professor Suzanne Cory. Among her many distinctions, Suzanne was the second woman to be elected as President of the Australian Academy of Science. This year, the medal was awarded to John Endler. It's a special privilege for me to honour John, who's a former colleague. I'll now read his official citation. John Endler is a world-leading evolutionary biologist. His research explores the interplay between ecological, behavioural and genetic factors and how they affect geographic variation and the process of natural selection. His contributions are wide-ranging and seminal. His scholarly books on how geographical variation can develop despite movement between habitats and his hypothesis of sensory drive are classics. The latter proposes that the environment sets the direction of the combined evolution of senses and signals, as well as mate and microhabitat choice behaviour. He pioneered this new interdisciplinary field of sensory ecology. John Endler has worked with a variety of species, notably wild guppies and bowerbirds, and topics from population genetics and evolution through to behavioural ecology and physiology. He defined the properties of bird and animal eyes to understand visual perception and visual illusions, and the importance of colour perception in mating success and sexual selection. Congratulations, John. John has been in the field in central Queensland, so was not able to record his presentation, but we're thrilled that we can still hear about his research. Enjoy.
How mating displays take advantage of animal visual system properties. John A. Endler. The mating process. There's a lot more to mating than mate assessment. The signaller S, usually a male, has to make itself conspicuous enough to be noticed by the receiver, R, usually a female. Then S needs to attract R's cognitive attention. Then S needs to hold R's attention long enough for mate assessment. Mate assessment, the only thing which is studied in many cases, consists of the usual three components. In parallel with mate assessment, the signal-noise ratio must be high enough, detectable and clear for attention, assessment and stimulation. This may allow illusions to change perception, and perception is needed to hold R's attention long enough for stimulation to mate. After assessment, it is also important to be in the correct environment, not only to minimize disturbance, but also that R's attention can be held. The stimulation needs to be correct for actual mating. Lots of unexplored interactions and two items are not well studied: holding R's attention and illusions which alter R's perception. My first example will be about bowerbird illusions, used to gain and hold the female's attention. Bowerbird males construct and decorate a structure, the bower, only used for attracting females for mating in the bower, rather like a teenager's car. The female watches the male on the court at the end of the avenue, while she is inside the avenue. She can only see part of the male when he leans into her field of view, either showing her an object, like the paperclip, or his nutshell or neck crest. The bower has a number of properties which can alter the female's perception in various ways: narrow field of view, display objects, and most of male outside the field of view until he flashes them in the field of view, and a size gradient with larger items further away from the female in the avenue. During the male display, the male peeks into the female's field of view with an object, see the photo on the left, or his nutshell crest facing here, as in the movie. During the male's display, he moves in and out of the female's field of view, showing off his nutshell crest and objects, and tossing the objects across the field of view so that they only show for a few seconds. Coloured objects, shown for a short time, have high colour and motion contrast against the grey court surface. Mapping of the courts in multiple bowers shows that almost all coloured objects are on the court outside the female's field of view, only showing when he picks them up to display them and then tosses them to either hidden side. The hidden location of the coloured objects is very important. When we move them into the field of view, they were placed outside the field of view in 2 days. An interesting pattern is that the size of the objects increases with distance from the female in the bower centre. This causes forced perspective, because increasing size with distance results in a very similar visual angle of all objects. Increasing size with distance results in the same visual angle, and we can see this as a very regular pattern of the court, seen through the avenue. Rearranging the court objects destroys the regular pattern, but the birds repair the gradient within 2 to 3 days. Like coloured objects outside the field of view, this is important to them. What does forced perspective do? Number 1, it makes a more even mosaic pattern. Number 2, the even pattern may make the male's nutshell crest and/or his waved ornaments more conspicuous than if they were seen on a random mosaic. The Ponzo, Ebbinghaus, Titchener, and Mueller-Lyer illusions are known in birds. If bowerbird perception is similar, the gradients, number 3, may make the court appear smaller and hence display objects and nutshell crest appear larger. Number 4, conflicting perspective and motion parallax depth cues may hold the female's attention longer than if the gradients were absent and may generate other illusions. Number 5, the nutshell crest and coloured ornaments waved over the court are similar in visual angle to the caught objects and may participate in the Ebbinghaus-Titchener illusion and therefore may change apparent sizes as they are moved. This is a simulation of the relationship between the static geometry and what happens when the female's head moves as in the movie. Without the movement, the caught looks smaller than it is. Note how if the gradient is reversed, negative slope, the caught looks a lot larger. If smaller than the male and his objects look larger. However, with the movement, there is a conflict of cues, and this could hold the female's attention. A third trick affecting perception is that the birds chew up plants to make a reddish paint and put this on the inside of the avenue wall, at bowerbird eye level. This results in chromatic adaptation. The way the retina is wired, this means that sensitivity to red is decreased, but sensitivity to green and UV blue is increased, as well as hue shifts to purer colours towards dotted lines on the graph. Brown backgrounds, avenues, go towards or stay in the grey perception area, dashed ellipsed. This greatly increases the colour contrast of the displayed objects and the nuptial crest. This shows how quickly chromatic adaptation happens. It's universal in vertebrates. Stare at the black dot between the squares on the left for at least 10 seconds, without moving your eyes at all. Then jump back to the black dot on the right. Note the shading and colours which appear in the white box. Light adaptation becomes stronger the longer your cones are receiving a constant radiant spectra. Switching animals, here is an example of a perceptual trick resulting from the interaction between pattern geometry and motion, something else which is poorly known. Guppies are variable for a mosaic of coloured patches of various shapes and sizes. During courtship, the body is rapidly oscillated around its long axis and also moved up and down. At other times, swimming, foraging, escaping predators, the motion is along the long axis. Motion can reduce the visual acuity or resolution along with the direction of motion. For guppies, at least the difference in motion direction has profound effects on the perception of colour patterns. Horizontal motion as well as horizontal stripes make it difficult for a pursuing predator to track the guppy. Most of the horizontal stripes are black, and black is much less affected by motion than chromatic colours because motion detectors only respond to luminance and not the colour. The pattern is much more complex and detailed during courtship displays, which may make it easier for females to assess the males in multiple ways. We don't know how often there is an interaction between motion and pattern in any animal. There are many ways that the visual system's existing properties can be taken advantage of during courtship or other visual interactions. Number 1, adjusting the receiver's field of view. Number 2, forced perspective and other perspective modifications. Number 3, active use of visual illusions which alter perception of sender. Number 4, chromatic adaptation, which can alter perception of colours. And number 5, interactions between colour pattern geometry and motion. There's a lot more to signalling than visual contrast. Similar effects may occur in other sensory modes.
Thank you very much for that presentation. And thank you, Paul Richards, for voicing that for us. Professor John Endler, as Helene Marsh mentioned earlier, is in the field and wasn't able to directly present that. However, we have been able to get him on the phone with us, so we hope the phone line holds so we can ask a few questions. Professor John Endler, congratulations. I'm hoping you can hear me.
Thank you very much. It was quite a pleasure to receive this award. Quite surprising too, but I'm happy about it.
Richly deserved.
Congratulations to the other winner too. I was glad there were both of us.
Thank you, John. Between Suzanne von Caemmerer and yourself, you are richly deserving winners of the Suzanne Cory Medal in 2021. I'm going to ask the audience if they would like to ask any questions to please pop those in the Q&A section so I can ask them of you. And we hope we can get through as many as possible and that the phone line holds. So I'll start off. The bowerbirds certainly have very unique and distinct mating rituals. Is that what makes them such a good subject to investigate evolutionary biology?
Well, it does, because one could actually make experiments in the wild without disturbing them, because everything that I've done experimentally in the wild is less intense than they do to each other, because they come along and steal each other's ornaments and trash each other's power avenues and do other obnoxious things, rather like people. So the fact that I can do field experiments is really unusual, because normally in the field you can't do experiments, and in the lab you can do experiments, but they might be totally artificial and not that related to what the animals do in the wild. So they're quite well positioned to do experiments.
Yeah, thank you. And what were some of the most interesting observations you made while studying the bowerbird?
Oh, that was mostly what my talk was about. The one thing I'm just working on now is whether or not the avenue focuses the sound and has further interesting auditory effects in addition to the visual ones.
Suzanne Cory has asked a question. John, congratulations, and where are you and what are you doing there?
I'm in North Queensland looking at bowerbirds.
There we are. The Suzanne Cory Award presented live during field research. Oh, fantastic. And so you're advancing, obviously, some of the observations and work that was presented. Is there a particular direction that's going in?
Yes, the sound effects caused by the bower on the female.
Fantastic. There were some very sophisticated techniques used by the male, including forced perspective. Were you surprised at how complex they were?
I was very surprised. The first time I saw the evidence of forced perspective, I couldn't believe it, but then I realized what it meant and tried doing experiments, and it turned out to be very important to them.
Yeah. Absolutely fascinating. And are visual cues the most important for gaining the female's attention in the bowerbird?
It might be, but there's a lot of sound going off, and that's why I'm currently investigating that aspect of it, because multimodal signaling could be quite widespread, but different species of animals use different combinations of signals, so one can't generalize too much, but it certainly is interesting.
All right, thank you, John. A question from Ron Eggers. If the bowers are so useful, why don't other bird species use anything similar to a bower?
That's a really good question. The only thing, well, actually, some birds make fancy nests, which are used as display grounds. There are some weaver finches in Africa that come close. There are also some spiders and some fish that come close to doing the same thing. Mm-hmm. But it's odd that it's only in Australian bowerbirds and nowhere else in the world.
Right. And thinking of it in an evolutionary sense, how can understanding the bowerbird's mating ritual help explain their evolution and process of natural selection?
Well, because each bowerbird has a different set of displays, it's sort of a model for how species diverge in their mating signals, and the more divergent they are, the more likely they are to not hybridize and go off in their separate evolutionary directions.
I see. Thank you. I learnt in your presentation that guppies use visual cues to escape predators and move in a different way when courting. Do you know why one direction is more effective than the other for each scenario?
Well, this is a fact of history, because if guppies had started out with a horizontal display and a vertical escape motion, which some other fish do, then probably their color patterns would have a totally different geometry. And in fact, generally for all species that use visual displays, there probably is a very close relationship between the movement patterns and the geometry of the color patterns. And that really hasn't been investigated. So I'm hoping this sort of thing will stimulate people to do that.
Yeah, fantastic. And in terms of application to other animals, would these kinds of discoveries be useful in identifying similar behaviours in other animals?
Well, yes, because no one has investigated the possibility that there's an interaction between motion and color patterns. And also there's a possible interaction between other sensory modes that we don't know. These give some of the early cues on what sort of interactions may take place.
It's absolutely fascinating. Do you have an opportunity to speak with younger students about your work? I don't know if time even allows that, but it's such a fascinating area of study that many could relate to just by being in nature.
Well, I just retired, so I can't formally have students, but I still answer questions from students all over the world. That's the lovely thing about email. It makes it possible to carry on some fairly detailed discussions with people. The most recent one was in Uruguay.
Right, fantastic. It's absolutely fascinating and so inspirational. I can imagine many primary and secondary students being fascinated across the world, and imagine being in North Queensland. Go on.
In fact, many secondary students actually email me too and asking questions and asking for advice on their projects, which I'm happy to do.
Oh, fantastic. You've influenced many school projects. All strength to you, and may it inspire those students to pursue science and evolutionary biology.
I hope so, yeah.
Yeah, you've spoken about some of the future directions of your work. Are there any new novel areas that you'd like to investigate beyond the Baobab?
Well, the broader question about the interaction between motion and geometry of color patterns, yes.
Yeah, fantastic. And just a personal question, what does winning this award, the inaugural Suzanne Cory Medal, mean to you?
Sorry, what did you say?
What does winning this award, the inaugural Suzanne Cory Medal, mean to you?
It means a lot. It means I'm actually getting recognized in a way that I never expected to be recognized. It's wonderful.
That's wonderful, John. Thank you so much. I'm so pleased we were able to connect with you today. I thought there was some chance we couldn't make that happen. It's an absolute pleasure to speak with you directly, and I know our audience members would feel the same. Congratulations again on being the joint winner of the Suzanne Cory Medal this year. Thank you for your time.
You're welcome. Anyone who wants to email me about these things, they're very happy to take their questions.
Oh, thank you.
So thanks again.
Thanks, John.
Okay.
Bye for now.
You're welcome. Bye.
Well, that brings us to the end of our event this afternoon, and what an inspirational and exciting event it's been. I've really enjoyed hearing about the breadth and depth of research by our awardees. It is always fascinating to know more about their work and see the impact of science across the globe. I would like to thank everyone, wherever they may be in the world, for joining us to celebrate Australian science and the work of our extraordinary awardees. Thank you again to all of our Science at the Shine Dome 2021 event partners. Our next Science at the Shine Dome events will be in November to celebrate the Australian Academy of Science's new fellows, so stay tuned to the Academy's social media channels and our website to find out more. We hope you'll be able to join us. That's all for today. Thank you for joining us. My name is Anna Maria Arabia, and we'll see you next time.